Okay, good morning, everyone. So last time we were talking about the very sudden approximation, and this is the first of several different approximations we'll be talking about for time-dependent problems. But we're starting with a relatively simple example of time dependence, which is that at some time, which we might as well call time t equals 0, the Hamiltonian, which had been h0, changes into something else that we called h0 prime. And we also had a slightly more general case where at time t equals 0, for a short time, it turned into something else again. But that was the sudden approximation. This is the very sudden approximation. And what's important about these Hamiltonians, h0 and h0 prime, is that in each case, we are supposing that we know the stationary states. Now, in the real world, that might be in some approximation, but we know them to the extent that we need to know them. And we want to know, how does the state of the system transition from what it was before time t equals 0 to what it is after t equals 0? So that's given by something called the transition amplitude. And for the next couple of weeks, we're going to be, not just in this situation, but in many other situations, figuring out how to calculate transition amplitudes. So in this case, we're talking about the transition amplitude for stationary states of the Hamiltonians that we know. Okay, and we write that as A sub n goes to m prime. And we write it, in this case, it's just the matrix element m prime with n. Okay, so if we start in the state n, it's a stationary state. So before time t equals 0, it's just evolving by multiplying by some time-dependent phase. And then it transitions into the state m prime of a different Hamiltonian. And then the probability of the transition is just the square of that amplitude, which comes right out of the postulates of quantum mechanics. Okay, and so that in this example is m prime n. Okay, so last time we had started with this example where this is really sort of a toy problem where you take the spring constant or the angular frequency of a harmonic oscillator and you double it. That's what you're doing when you're changing your Hamiltonian. Okay, and we're not asking why it doubles or how it doubles, it just doubles. Some external agent doubles it. And we want to know, if you started out in the ground state, what's the probability that you will remain in the ground state? So what is probability of remaining, implying that you were there already, in the ground state? Okay, and we can't be fooled by the terminology because it's a different ground state. In fact, that's sort of the whole point. So before the transition, let's do this in terms of wave functions. The wave function for the ground state of the harmonic oscillator with angular frequency omega is, we look back and we discover it was this thing, m omega over pi h bar to the 1/4. Okay, exponential of minus m omega x squared over 2 h bar. So it's a Gaussian wave function in x with some funny factors that depend on h bar and the mass and things like that. And then the state after the Hamiltonian changes, if it's in the ground state, has this wave function. So we just replace omega everywhere by 2 times omega. let's go ahead and do that. Okay, and so we have exponential minus m 2 omega x squared over 2 h bar. And so in this case, the transition amplitude to go from the ground state with frequency omega to the ground state with frequency 2 omega is this matrix element. And the reason for writing down the wave functions immediately above it is because now we can compute this thing in the position representation by using the wave functions. Okay, so we integrate over all x and we plug in 2 omega 0x, x0. Okay, and I forgot my factor of 1/4 here. So this is equal to, pulling out the constant, there is a square root of m omega over 2 h bar. But we can't forget that there's an extra factor of 2 here, which comes with a 1/4 power. So let's write that down, 2 to the 1/4. And then everything else we can't pull out of the integral. Namely, there's an exponential of minus m omega over h bar times x squared. And then there was a factor of 1/2 in the exponential from here and 2/2 from here, so that makes 3/2. Okay, so there's a factor of 3/2 here. All right, so that's an integral you can do or look up. And the answer to that is square root of 2 pi h bar over 3m omega. And so when we put this all together, it's 2 to the 1/4, 2 to the 1/2 from doing the integral, divided by 3 to the 1/2 from doing the integral. And the m omegas and h bars all cancel. And so what we get is that the probability for this transition to occur is the square of the transition amplitude, which in this case is going to be 2 square root of 2 over 3, which turns out to be about 94% chance, roughly. So whenever you're doing a problem like this, it's important at the end to do 2 checks, because if you're calculating a probability, the first thing is it has to be a dimensionless number. Probabilities are dimensionless numbers. They're not things with units of energy or anything else like that. And so indeed, that's what we got. It's 2 square root of 2 over 3. So that worked. And it should also be between 0 and 1. All probabilities are necessarily between 0 and 1 inclusive. And indeed, this one was. Okay, so let's do a more practical example. That one was sort of a silly toy example. So a more practical example is tritium decay. And this is, in fact, a classic example of this in action, of the sudden approximation in action. So what's tritium? Tritium is the atomic weight 3 isotope of the hydrogen atom, hydrogen nucleus. And so it consists of 3 nucleons, namely 1 proton, that's what makes it hydrogen, and 2 neutrons. Okay, and the atom, therefore, is going, if it's neutral, is going to contain 1 electron to match the proton. And so this is something that we can use our formulas with atomic number 1 when we studied the hydrogen atom. So if you have tritium and you study it carefully, you will find that it has a half-life, by study I mean experimentally study it. It has a half-life of about 12.3 years, which is a very long time by decay standards. And when it decays by beta decay. Beta decay is code for saying it decays in the following way. Your tritium nucleus decays to a helium nucleus with atomic weight 3 plus an electron. Okay, the hydrogen has charge 1, the helium has charge 2, so to balance the charge we need an electron. And then there's another particle that's emitted called an antineutrino, like that. And so we're decaying to an atom that has Z equals 2 plus 1 atomic electron. That atomic electron is this electron that was there originally. And then we're getting a beta decay electron here, so another electron. But the point is this electron is going to leave the atom extremely quickly. So that's very important. So let's check why that's true. And the neutrino doesn't count because it has no charge. It doesn't interact with anything. It just leaves without doing any damage. So why does this thing leave the atom very quickly? It's because if you calculate how much energy it has, which you get by looking at the difference between the 3 hydrogen and the 3 helium energies, the energy is up to 0.0186 million electron volts. And the average of the energy carried by that electron is roughly a third of that. But if you compare that to the rest mass of that electron and do some relativity, you find out that the speed of it is, the maximum is about a quarter of the speed of light. And the average, we're just plugging in the energies here. Okay, so the average speed it has is about 15% of the speed of light. And those things are to be compared to the average speed of an atomic electron in hydrogen. And when we studied the hydrogen atom, we found that the average speed, which we kind of define by the average momentum divided by the average mass, and we define the average momentum by the expectation value of the momentum. So in any case, order of magnitude, this is the fine structure constant times the speed of light. But the fine structure constant is about 1 over 137. So that makes it 0.0073 times the speed of light. Okay, and so the moral of the story is this electron that's produced, the beta decay electron, is produced with a speed that's much, much larger than the speeds of the electron that was already there. And so for all purposes, it leaves the scene very quickly. Before anything else in the problem has a chance to react to it. And so we can just sort of ignore it. So when we're talking about the electronic state, the final electron state, we're really worried about this atomic electron here. And this one we can just ignore. So that means we can go ahead and do the sudden approximation. Okay, and so if we start in the ground state of tritium, and we ask what's the probability of ending up in the ground state of 3 helium, so probability of ending in ground state of 3 helium. That we get by just using the sudden approximation, which means we take a matrix element squared. And here's what the matrix element is going to be in the position representation. So we have the state that we're ending up with, which is the 1, 0, 0 state of a Z equals 2 atom. That's 3 helium. And I'm putting the complex conjugate there because morally it's there, even though this is actually a real wave function. And then the state we're starting off with is the 1, 0, 0 state of the Z equals 1 tritium atom. Okay, and so that's the amplitude, and to get the probability, we have to square it. Okay, so we've boiled it down to doing some integral, and to do the integral, recall or look up that the 1, 0, 0 state for a general atomic number is the following. It's 1 over square root of 4 pi, 2 over the Bohr radius divided by the atomic number to the 3/2. There's different ways of writing this, times the exponential of minus ZR over the Bohr radius. So when I write that, the 1 over square root of 4 pi is actually the spherical harmonic y0, 0. And it's because we're in the L equals 0, M equals 0 state that we just get this very simple spherical harmonic, which is just 1 over square root of 4 pi. But both the initial state and the final state have that. Okay, and so let me do it this way. Let me call the stuff before we square it. As usual, we'll call that the transition amplitude A. And so A is equal to, since nothing in this problem depends on the angular coordinates, I'm just going to multiply a 4 pi for integrating over the angular coordinates. Okay, and then I do dr r squared. I can't forget that there's an r squared for volume integrals. And then both of the things in there have a 1 over square root of 4 pi, so I square that. Both of them have a factor of 2, so I square that. Okay, and then one of them has a Bohr radius over 2 to the 3/2. The other one has just a Bohr radius to the 3/2. And one of them has an e to the minus 2r over Bohr radius, and the other has e to the minus 1r over Bohr radius. So that factor, when I combine them, when I multiply them together, it looks like that. Okay, and so if we combine all the constants, notice the 4 pi's go away. How many factors of 2 do I have? I have 7/2 of them. How many factors of the Bohr radius? I have Bohr radius to the minus 3, so 1 over Bohr radius cubed. And then the integral we have to do is this one. So it's r squared e to the minus 3r over Bohr radius. And so you can look that up. And that's 2 over 27 Bohr radius cubed. So multiplying those two together, this is 2 to the 9/2 divided by 3 cubed. You often get these powers when you're dealing with a hydrogen atom, you get these powers of 2s and 3s. So that's the amplitude, and therefore the probability is just the square of that. So that's going to be 2 to the 9th power over 3 to the 6th power, which turns out to be 512 over 729. And as a decimal, that's about 70%. Okay, and notice that the Bohr radiuses canceled, as they had to, because this had to be dimensionless. It's a probability, has no units. Okay, and it's less than 1. Okay, so that was the probability to start in the ground state and remain in the ground state. Another thing you could ask is, what's the probability to end up in some other state? So let me do an example like that. So let's ask, what's the probability to end in a state like, I don't know, n equals 16, L equals 3, and M equals 0. Okay, and the answer is I've chosen that very carefully because it's going to be 0. So let's just remark on why it's 0. The answer is 0 because what am I calculating? I'm calculating the z equals 2 state, n equals 16, L equals 3, M equals 0. Matrix element with the n equals 1 state, L equals 0, M equals 0, for z equals 1. Okay, but there's no way for that to be non-zero because there's no way that an L equals 0 state here can have any non-zero matrix element with an L equals 3 state. Okay, so that's just 0 by angular momentum selection rule. Okay, so for homework, you get to calculate a couple of things that aren't 0. Although when I worded the problem, I didn't tell you anything about angular momentum. So this right here will tell you what you do and do not have to think about. Some of the things that you might try to calculate, if you think about them ahead of time, will be just 0 because they don't conserve angular momentum. And so you get to calculate the n equals 2 transition and the n equals 3 transition. And so things you should check, as you're asked to check in the problem, is that the total probability, when you add those things up, first of all, again, has to be dimensionless, but also has to be less than 1. So if you happen to get a number larger than 1, it means you may have dropped a factor of 2 or 2 to the 7th or something, and you should figure out what happened. Okay, any questions on those examples? All right. So we're getting ready to do time-dependent perturbation theory in a general way, but it's useful to first set things up by talking about pictures in quantum mechanics, something we haven't talked about yet. Pictures is just a jargon for different ways of organizing time dependence. So different ways of organizing time dependence. Okay, and there are 3 pictures that are generally talked about. There's the Schrodinger picture, and there's something called the Heisenberg picture. And there's the one that we're really going to find useful is called the interaction picture. But all 3 of those have too many letters. And so I will typically abbreviate them by S and H and I. I is also known as the Dirac picture. Okay, and so the H we're going to have to be a little bit careful of because H we always think Hamiltonian, but now it's going to mean Heisenberg. And so the first thing we need to know is that everything we've done up to now in this course has really been in the Schrodinger picture. So far, we've been using Schrodinger picture, which I just write as the H picture, S picture. And what does that mean? That means states evolve according to IH bar time derivative, this was one of our postulates, is equal to the Hamiltonian times the state. Okay, that was postulate 6. But we could have said, when we said postulate 6, we could have added the words in the Schrodinger picture, but that's what we usually use. So we didn't bother with that terminology back then. So way back when we were studying this stuff, we then realized the consequences of this because we could write down a solution. The solution for the Schrodinger picture state is a unitary operator times the initial state, which we're talking about at time t0. So that initial state is an initial condition for our differential equation. And U, we've worked out, was a unitary operator. So that's useful to know, even if we can't solve for it exactly all the time. So unitary operator means that its inverse is equal to its Hermitian conjugate. And as a bonus, that's the same thing as if you interchange the initial time and the final time. And when you plug that into this differential equation, then you learn an operator differential equation. So this is review. So IH bar d by dt of the operator is equal to the Hamiltonian times the same unitary operator. So that's generally true. It doesn't make any assumptions. But if you make one more assumption, then it's easy to write down the answer. And that assumption is that the Hamiltonian is constant. Okay, then the solution is easy. It's easy in the sense that we can just write it down and then plug it in to check that it works. Okay, and it's the exponential of minus IH t minus t0, all divided by h bar. So if that was all there was to it, if we were only interested in constant Hamiltonians, there really wouldn't be any point in talking about the other pictures, because we've just written down the answer. There's not much more to do except evaluate the Hamiltonian and evaluate its exponential. But the point is that the Hamiltonian is not always constant, and that's what we're getting ready to work on. Okay, so in the Heisenberg, and this is the last time I will spell out Heisenberg picture instead of just writing H picture. So the idea is to transfer the time dependence from the state to the operators. So transfer time dependence from the state of the system which we're going to call it psi, pretty much universally, to operators. Okay, and we do that just by making a definition. We're going to define what our Heisenberg picture states and operators are. So first of all, the state in the Heisenberg picture, we're going to define by the unitary operator, except with a dagger, acting on the Schrodinger picture state. Okay, now if we go back up here, we realize that in a way, if we just take U dagger and multiply by this equation, okay, then we will get this with psi evaluated at time t0. So this is psi t0 in the Schrodinger picture. Now, that's a constant in time because it doesn't depend on time. It only depends on t0, which is some reference time. So this is a constant in time. Okay, so what does that tell you? That tells you the Heisenberg picture state never changes. It's always equal to its initial value, which also is the Schrodinger picture state. So to make everything work, we have to simultaneously define the Heisenberg picture operators, which we do by, again, putting a U dagger in front of the Schrodinger picture operator. But then we put another U after it. This is just a definition. Okay, and so this is true for any Schrodinger picture operator. Okay, so as a matter of notation, what I've done here and what I will continue to do is if you see an H subscript, then it's the Heisenberg picture. And if you don't, then it's not. So if H subscript, and in the notes for variety, I did it a little differently. I used an H in parentheses superscript. But I decided in class that's too much stuff to write. Okay, then it's the Heisenberg picture. And if I write a state or an operator without those, then you automatically assume it's the Schrodinger picture. Okay, so if not, if no subscript, then it's the Schrodinger picture. So just going back up here I wrote a state, I didn't put an H, therefore you assume it's Schrodinger. I wrote an operator, I didn't write an H subscript, so it's Schrodinger, this is Schrodinger, and so this is saying the Heisenberg state at all times is equal to the Schrodinger state at time t0, which is why I didn't put a t there, even though I could have perhaps, but it doesn't change with time, so that's why I didn't bother. And then these are all Schrodinger picture operators, and this is how the Heisenberg picture operator changes in time. Okay, so the first thing we need to do is figure out why this is a useful thing. It's a useful thing because Heisenberg picture and Schrodinger picture have exactly the same physics. And there's one short calculation we can do to prove that. And that calculation is to notice that in both pictures, inner products and matrix elements, which are the things we use to calculate probabilities and therefore make predictions, are the same in both pictures. So we're going to prove this very generally, and it's only going to take 2 lines, so it's going to be easy. And then once you've proved it, then you know, since inner products and matrix elements are the same, any prediction you make for a probability is going to come out the same. Okay, so let's do it. Let's write down a general matrix element, and I'm going to write it for a state in the Heisenberg picture and a general operator in the Heisenberg picture, which might depend on time, and another general state in the Heisenberg picture. And so the first thing we're going to do is translate everything there into the Schrodinger picture. Okay, and so this is phi of t, u of t, t0.
I'm sorry, Professor. Is that one on the left? I just wanted to confirm. That's a phi, and then the one on the right is a psi, correct?
That is correct. I'm choosing them different because I want to do a general matrix element, not just an expectation value.
Okay, thank you.
Okay. So I'm translating to the Schrodinger picture, and so what I did here is I used for the phi, I used this relation, but because I'm doing it for a ket, and I mean, sorry, for a bra, not a ket, when I take the Hermitian conjugate, this U dagger changes into a U. Okay, so that's my, that whole thing is my phi H bra. And then my AH, I can just read off. It's U dagger. Schrodinger picture A, U. Okay, so those all go together. And then finally my psi H, again, I can just read off from here. And so that's going to be U T0 dagger times my Schrodinger picture T, running out of space there. Okay, so that's the original input, but then I remember, aha, UU dagger is the identity operator, and UU dagger here is also the identity operator. That's where unitarity comes in and is very important. And so this is phi of t, A of t, psi of t. And that's it. That's showing that the Heisenberg picture matrix element of any operator is equal to the Schrodinger picture matrix element of any operator.
Professor,
Yes,
I'm sorry, I lost you a minute. So that left one is phi. That middle one you said is A.
right. This is just AH of t.
And what's that right one is the,
So this is going to be psi h.
thank you.
Okay. All right. So we've proved that matrix elements are the same. Inner products, of course, are just special cases of matrix elements where you don't have an operator in between. So that would be just setting A to 1. Okay, and so we can conclude that the Heisenberg and Schrodinger pictures are physically equivalent. Okay. So one thing we can ask is when I've written the operators as if they depend on time, but sometimes they do and sometimes they don't. So often what will happen is you'll have an operator A in Schrodinger picture, which doesn't depend on time. But when you work out what the Heisenberg picture version of it is, it does depend on time. But you could ask, when doesn't it? Maybe sometimes it won't. And the answer is there's a special case when it won't. And that special case is, suppose you have the following properties. First of all, we're going to suppose that the Hamiltonian and A don't depend on time. Which is very often the case. For example, the hydrogen atom, the harmonic oscillator, the Hamiltonian for those doesn't depend on time, and say the momentum doesn't depend on time. Okay, so that's very often satisfied. But we also need the following property that they commute, which is much less often satisfied. For example, the momentum operator does not commute with the harmonic oscillator Hamiltonian. But suppose those things are true, then since the Hamiltonian doesn't depend on time, the unitary operator is, as we said, just this thing. Okay, and that also commutes with A. It also commutes with A because the only operator in it is H. And since H commutes with A, for all purposes of writing down things in different orders, they might as well just be numbers. They just move right past each other because they commute. And so if the unitary operator commutes with A, then when I write down my Heisenberg operator A, which is defined like this, notice that I'm often going to just leave off the T and T0 arguments when they don't make any difference. Okay, they commute, so I can write this as U dagger U times A. I just commuted the U past the A. And then U dagger U is the identity, so that's equal to A. Okay, and so the Heisenberg operator is equal to the Schrodinger picture operator, and the Schrodinger picture operator, we are assuming here, doesn't depend on time. Therefore, the Heisenberg operator also doesn't depend on time. Okay, and so that's called a constant of the motion, which is stealing some terminology from classical physics. They're really still operators, but they're constants. And so one good special case of this is when the operator A is equal to the Hamiltonian itself, then trivially it commutes with the Hamiltonian because it is the Hamiltonian. So in particular, if the Hamiltonian doesn't depend on time, then we learned that the Heisenberg Hamiltonian is equal to the Schrodinger Hamiltonian. Okay, and so they're both constant in time. So that won't necessarily be true if H depends on time, but as long as it doesn't depend on time, then they're the same thing. So now we can ask more generally, how do we know how the Heisenberg operator changes with time? Let me rewrite that more generally. How does our Heisenberg operator change in time? And so to find out, we're just going to do a little calculation here. So the thing we want to know is what's the time derivative of our Heisenberg operator? And to answer it, we're just going to take derivative of the thing translated into the Schrodinger picture where we know how things change in time. So when we do that, we're taking a derivative and we're using the product rule. And so there's one term that looks like this. Okay, there's one term where we take the derivative of the U dagger times A times U. And then there's another term where we take a derivative of the U that's at the end. And then the other thing is it might be that the Schrodinger picture operator also depended on time. We're no longer assuming that it doesn't necessarily. So there's also a contribution like that. So we've just used the product rule for taking derivatives. Okay, so what can we do with these things? First of all, on that last term is everything in the Schrodinger picture, but now we can translate it back to the Heisenberg picture because this is the derivative of the Schrodinger picture A with respect to time in the Heisenberg picture because we sandwiched it in between U dagger and U. For the others, we have to be a little bit more clever. Here we have to use, for example, the differential equation. So the differential equation for U tells us this is minus I over H bar Hamiltonian times U. And then if you take the Hermitian conjugate of that, the same thing works here. So this is I over h bar u dagger times h. And now we're going to combine those two. So this is I over h bar u dagger h a u minus u dagger a h u, which we can rewrite by between the h and the a and the a and the h, we're going to sandwich in a u dagger. We'll see in a moment why that's a good idea. So I just put a u dagger. That's equal to 1, so I can go ahead and do it. And then the other term is u dagger a u dagger hu. Again, I haven't done anything. I've just inserted the identity operator in a clever way. Okay, but then if I stare at that, I realize that's equal to I over h bar. The u dagger hu is the Heisenberg Hamiltonian. The second u dagger au is the Heisenberg A, and then I've got them in the opposite order with a minus sign, which I can then write as a commutator. So let me write it here as I over h bar commutator of Heisenberg Hamiltonian. And I've got to be careful because it may or may not be the same as the Schrodinger Hamiltonian commuted with h. So let's just put that all together and put it into a box because it's an important equation. The time derivative of the Heisenberg A operator, whatever it is the commutator of the Heisenberg Hamiltonian with it, plus an extra term, which involves the explicit time derivative of A. Okay, so just to comment on the meaning of this last term, suppose I gave you a specific A and I asked you to calculate this, what this was. The meaning of this is you take the derivative of A in the Schrodinger picture with respect to the explicit time dependence. That means the time dependence that's kind of built into the operator. Can't spell dependence. So this is in the Schrodinger picture. And then after you've done that, then you convert to the Heisenberg picture. That's what the parentheses mean. So then convert to the Heisenberg picture. That's the meaning of that expression. Okay, so that's worked out how a general operator in the Heisenberg picture depends on time. And the important thing to realize is that in the Heisenberg picture, that's all there is to know about how things change in time. And that's because in the Heisenberg picture, as we showed, the state never changes. The state of the system doesn't change ever. It just stays whatever it was. And so this equation for A, the operators, captures all time dependence. Okay, and so solving a dynamical problem in the Heisenberg picture amounts to, in some sense, amounts to just solving this differential equation for the operators. Okay, so one last thing before we stop for today is to ask about commutation relations because they're often important. This will be quick. So the commutation relations are the same in the Heisenberg picture as long as you do it at equal times. It's very important, so I'm going to underline at equal times. And again, this is going to be a short two-line proof. Suppose I have in the Schrodinger picture some commutation relation for two operators A and B. Their commutator is C. And then I decide to calculate the same thing in the Heisenberg picture. And the way we're going to do it is temporarily translate back to the Schrodinger picture. So this is going to be U dagger AU, U dagger BU. And then if you write out both terms in the commutator, this turns out to be just U dagger commutator A with B. Everything there is in the Schrodinger picture because I didn't put any subscripts. And so that's equal to U dagger C U, which we recognize is equal to the Heisenberg C operator. Okay, so the commutation relations don't change as long as this T and this T are the same thing. So where this fails is if they're different. Okay, so for example, if I do the commutator of X and P in the Heisenberg picture at equal times, I get I H bar just like I get in the Schrodinger picture. And a lot of times that's what you really want to know, but you just have to be careful because if I do this commutator, for example, Heisenberg picture commutator of X at time t with P at some different time t prime, that in general is not anything simple. And in particular, it's not IH bar. Okay, so that's why the at equals times is very important. All right, so we're out of time for today. We're a little bit past time, sorry about that. But next time we will continue talking about the Heisenberg picture. From my point of view, this is really all a warm-up for the interaction picture, which is the really useful thing that we will learn how to solve time-dependent problems with. Good, so are there any questions on today's lecture? All right, if not, then I will see you on Monday.
Professor?
And have a good weekend.
Professor?
Yep.
I just had a concern. Friday is the qualification exams, and the Thursday before Friday, this coming Thursday, is E&M midterm. Could you offer the courtesy of extending this Thursday's deadline